In this session, we are focusing in code-based transformation using script task. We will be using C#, so I am assuming you already have basic programming knowledge to follow along. To demonstrate how code-based transformation work, I built a minimal API that reads CSV file and returns the data as JSON through this endpoint. The API operates using two essential components, a service that reads the CSV file we worked with in previous sessions, and a model named sales order. It retrieves the dataset from the same CSV file used in our previous session. Now let's run our API by pressing Ctrl F5 to start our code-based transformation. As you can see, it opens a console window displaying the application startup log. This indicates that our API has successfully started. It also shows two automatically generated URL endpoints, one for the HTTPS port and one for the HTTP port. In SSIS, we will add new package and name it code-based transformations. Then we will add a script task component. Before we start modifying the script task, we will first add a variable to store the API endpoint URL. Then we will also add a connection manager. We will use Ado.NET instead of OLEDB so we can fully take advantage of the native .NET SQL related objects. Let's rename the connection manager. Now let's edit the script task. To pass the value of our API endpoint variable into the script task, we will add it to the read-only variables property. Inside the script task, we will create a method named callAPI. This method will contain the API request logic and handle most of the data transformation work. The main method will simply call this method and then return the control back to SSIS. Let's get the value of our endpoint URL from the variables collection. We will use the HttpClient class inside our callAPI method to call the API. But since the HttpClient assembly isn't referenced by default, we need to add it manually before we can use it. We will call the getAsync method and pass the API endpoint URL as the parameter. Since our callAPI method is not an async method, we will force it to run synchronously by accessing the .result property. Then we call ensure success status code to verify the API returned a successful response. If the API fails, SSIS will immediately throw an exception. Then we will deserialize the returned JSON data into a JSON element object. JSON assembly is also not referenced by default in the script task project. We need to add it manually as well. We also need to add the system memory assembly since JSON library depends on it. Now let's add a breakpoint and run the package to verify that we can connect to the API and successfully retrieve the JSON data. Now that we have confirmed we can connect to the API, let's copy the JSON result. We will need these property names in the next step when we write the code that parse each field from the JSON response. We can also verify the structure and properties of our API response directly through our API Swagger. The next step is to iterate through each item and map the fields into a strongly typed C# object. We will create an internal sales order class to represent the structure of the data we are pulling from the API. To make this easier, let's copy the property names from the model we created in the API project, but we will replace those string types with the actual data types used in our database table. We will loop through the JSON array and assign values to our sales order class properties. Since the JSON response may contain invalid values for some fields, we will make the corresponding properties in the sales order class nullable, specifically the order ID, order date, quantity, and unit price fields. This allows us to safely assign null when the JSON contains an empty string, an unexpected format, or any value that cannot be parsed correctly. Let's add each item to a list of sales order object and rerun the package to verify the added code is working properly. Now let's add the necessary validations to determine which record should be redirected to the exception table and which ones should be inserted into the sales order table. To check whether a region value exists in the region table, we will load all existing regions from the database and store them in a hash set of string objects. To do this, we will open a connection to the database using SQL connection object, execute the SQL command to retrieve the data, and iterate through the results using SQL data reader. We will also do the same for the existing order ID values. This allows us to quickly check whether an incoming order ID already exists in the database before deciding whether the record should be inserted or redirected to the exception table. To check duplicate order ID values in the JSON data, we store each order ID in a hash set of integer. A hash set only allows unique values, so when we attempt to add an order ID that already exists, the hash set.add method returns false. This return value indicates that the order ID is a duplicate within the JSON data, allowing us to flag the record and redirect it to the exception table. Now let's proceed with inserting the records into our database tables. To keep this organized, we will create another method that accepts two parameters, all validated sales order records and the non-existing region values. This method will encapsulate the logic for inserting valid records into the sales order table, redirecting invalid records to the exception table, and inserting any non-existing region values as new entries in the region table. Everything seems to be working correctly, so we can now proceed with building our insert to database method. For inserting records to the database, we will perform a bulk insert using SqlBulkCopy. This approach allows us to insert all records into the database in a single operation, making the process significantly faster compared to row-by-row inserts. Let's do the insert to the region table first. Before we can perform the bulk insert, we first need to create a data table to store the records from our parameters. The data table will serve as the staging structure for SqlBulkCopy, since bulk insertion requires a tabular dataset that matches the schema of the target database table. For the sales order insertion process, we know that records will either be inserted into the main sales order table or redirected to the exception table. To handle both insertion cleanly, we will apply a for loop that iterates twice. During each iteration, we will store the loop counter in an integer variable and use a ternary operation to determine whether the current pass is for inserting exception records or for inserting valid sales order records. And since the sales order and exception tables share the same column structure, we can just create a single data table that will serve as a staging table for both insert operations. Now let's test the package by clearing the data from our tables first. This ensures we are working with a clean slate and can accurately verify whether the insertion logic behaves as expected. All records were inserted correctly. Next, we will add rows in the CSV that contain non-existing region values and run the package again. As expected, the new regions were successfully inserted into the region table, and all invalid records were correctly routed to the exception table. Now we will add records with invalid values. Invalid records were inserted into the exception table without any errors. Next, we will add duplicate records to our CSV file. Only one record was inserted into the sales order table, and the remaining duplicates were correctly routed to the exception table. Finally, we will add records with valid data to verify that the process is inserting records correctly. All records have been inserted correctly. That completes our code-based transformation tutorial. Now, let's compare the three ways to perform data transformations in SSIS. The component-based method is the classic SSIS approach. It uses drag-and-drop transformations inside the data flow task, making it visual, easy to learn, and great for standard ETL patterns like lookups, merges, conditional splits, and basic cleansing. The stored procedure-based method moves the transformation logic into SQL Server. SSIS loads data into staging tables, and SQL handles the heavy lifting. This works best for set-based operation, high-performance workloads, and environments where business logic belongs in the database. The code-based method using a script task offers maximum flexibility. You can implement custom logic that SSIS and SQL Server cannot handle natively. It is ideal for external integrations and API-driven workflows. Now let's talk about the pros and cons of each method. For the component-based method, it is the easiest to learn and visualize, no coding required, and great for standard ETL patterns. However, it has limited flexibility, it is hard to manage complex logic, and the performance drops with very large datasets. On the other hand, stored procedure-based method has excellent performance for large datasets, centralized logic inside SQL Server, and easy to maintain for DBAs. It is ideal for set-based operations. But it requires SQL expertise, logic becomes database dependent, it is harder to integrate external systems, and SSIS becomes mostly a transport layer. The code-based method has the maximum flexibility. It can call APIs, external services, or custom libraries. It is perfect for modern architectures and has full control over validations, routing, and transformation logic. However, it also requires C# development skills, more moving parts, debugging can be more complex, and performance depends on code efficiency. Understanding the strengths and limitations of each method helps you choose the approach that best fits your project. If you want simplicity, the component-based method works well. For performance and centralized logic, the stored procedure-based method is the strongest option. And for flexibility or modern API-driven workflows, the script task approach gives you full control. Each method has a place in real-world ETL work, and knowing all three lets you build SSIS pipelines that are both adaptable and effective.